you've encountered me on GitHub. You may know me as Effigies, and so these slides are all available on GitHub from the Testing Scientific Software page. Okay, so a quick outline of how this talk's going to go. I'm going to give a cautionary tale, define some terms, give a quick look at pytest before then moving on to talk about numerical testing, how to generate test data, some useful testing tools, and then some specific concerns that come up in the neuroimaging context that when writing tests you should be aware of, or really when writing software you should be aware of. So the cautionary tale comes from UCSD, and I want to say this was around 2005. The lab of Jeffrey Chang is molecular biology, and they ended up having to submit a retraction of a paper, and this was resulting from an in-house program introducing a change in sign. And unfortunately, the procedure still allowed them to obtain reasonable results. And the part of the problem here is not just that it was embarrassing for them, but there is a consequence outside their own lab. So we sincerely regret subsequent research efforts that were unproductive as a result of our original findings. So I think this is instructive about the importance of testing. So to put a finer point on it, when writing scientific software, what are the reasons for testing? The first is just to check your work. Does this thing do what I expect? If there are good known results for a certain set of inputs, does my method reproduce those results? And if I put in novel inputs, do those at least produce reasonable results to the extent of my knowledge? Some of it is just helpful for clarity of thinking. The code is one specification of a scientific method that you're trying to promulgate, and another way of specifying it is putting constraints on defining what are my inputs, what are my outputs. And it's just basically lets you work on the problem from two ends at once, and that's somewhat prophylactic against failures like previously mentioned. And there's also just additional assurance. If I write tests for a large portion of my code base and then I want to go through and make changes, I can have a lot more confidence that I'm not breaking anything substantial if I'm able to rerun all of my tests again and see that they continue passing. So I'm going to talk a little bit about define some terms here. So you'll run across various ways of talking about tests, and one phrase you'll hear a lot is unit test. And this is just code that validates that some component or unit of your code works as expected. And this is often considered really small units, individual functions, maybe a class. And so you check that a function produces expected outputs for known inputs. You verify passing impermissible inputs raises a sensible error that a user can interpret. Then there's integration tests. And this is when you're trying to take two smaller units and make sure that they work together correctly. And in practice, this ends up looking just like a more complicated unit test. You're now having to consider a wider range of possible inputs and like combinatorial inputs. And then there's regression test, which is, I think, when you're starting to contribute to a project is going to be the most common type that you're going to write, which is, I found a bug. I'm going to write a small piece of code that shows that the bug exists, and I'm going to call that a test. Now, when I submit my fix, this test should now start passing, and this is a way of demonstrating that it works, and also so that if somebody makes a change in the future, you'll be able to quickly see whether that bug is reintroduced. Another phrase that you might hear a bit is a smoke test, and this comes from the electrical engineering world, which is basically plug the thing in and turn it on. If it starts emitting smoke, turn it off, unplug it, and you don't really need to test anything more in depth. You know something has gone horribly, horribly wrong. So there are some very, very basic tests that you want to run before you bother with all of your really detailed tests. So for instance, one time we released a version of Babel that if you didn't have some test, I think it was a test library installed, then you couldn't even import it. And that was that. So we added a test to make sure that when you install so we didn't catch it because, of course, our tests, when we run the tests, the test software is obviously installed. So we make sure that we can import before we install the test software, for instance. So a bit more terminology, and just because you're going to see this a lot. You might not see the phrase xUnit, but you're going to see the vocabulary that derives from it a lot. So xUnit is a model of tests based on the Smalltalk xUnit library. And they introduced this structure and vocabulary. And so the X is for whatever language you want. So in Java, I think they have JUnit. And so all of the main Python test runners which are unittest, pytest, and nose are the big ones. And they're all xUnit compatible, which means they basically use the same concepts and structure. So the first thing that you have is an assertion, which is really your basic, this is your atom of tests. You check that a thing is true or not true. If it's not true, then you raise an error that your test fails. Test case this is going to be your unit test, and this is going to often be a series of assertions. I run a function and then I make sure the outputs look like, have properties A, B, and C. Fixture, this is one that comes up and I think is often poorly explained. This is just the processes that happen before and after a test is run. And so some tools make this more or less explicit. A good example of a fixture is if you want to create a temporary directory so that your test can, pollute the file system all at once, and then after the test runs, it'll make sure you're not in that temporary directory anymore, and it'll delete the temporary directory, and you leave the file system as clean as you found it. But you can do a lot more things with that, obviously. And then test suite is just a set of test cases with a common fixture. I'm not sure that in Nilearn we really use this particular concept, but you might see that. Okay, so if you haven't run tests in Nilearn, but you do have both pytest and Nilearn installed, you can actually run the tests directly using this pytest pyargs Nilearn. So what this will do is it will find all of the modules that begin with test or end with test, and then find all of the functions or classes inside it that have test at the beginning of the name. And it will also find anything from unittest.test case that's a particular structure. I don't think Nilearn uses that, but in case you're interested. The more common way to do this is you actually have your source directory, and then you just run pytest on your source. And this will do, for most software, it will end up doing exactly the same thing. There may be some tests that are only really feasibly run from the source directory. For instance, you might have some test data files that you don't want to package with the actual installed version, but you want there for more complicated tests. Okay, so I'm going to step back for a little bit and now start talking a bit more conceptually about how you do numerical testing. Maybe I'll stop for a second, make sure there's no questions. Nope. Okay. So I'm going to assume that pretty much everybody who's working with Nilearn is going to be at least vaguely familiar with NumPy. And just up here in the top right, if you're following along, which I don't really recommend trying to do, but if you're following along on your own at home later, I just put imports that I don't want to put in the middle of the screen and take up space up in the top right. So NumPy arrays work with your usual equals, not equals, comparison operators, etc. And the way they do it is they work element-wise. So I have a list of 5 integers from 0 to 4, and then I have a reversed list. I can check whether they're equal, and it will only say, so 0 and 4, 1 and 3, 2 and 2 are equal, and in the reverse, these are not. And then you can also generally compare an array to a scalar. So I can check which of these is equal to 3. So 0, 1, 2, 3, 4, 3 was equal. Just to give you a little bit of vocabulary in case you don't have it, this is an example of broadcasting. If the NumPy rules for comparing can be a little complicated. So if I have two arrays that are not the same shape, sometimes I can still make them work together, and that's because NumPy will broadcast them. So this can either be extremely handy, or it can be a major trip up. So just be aware that when you're not checking the shape directly, you are probably going to be running into these implicit rules, and so that's also a thing you might want to check to make sure that you're doing right, and possibly with the test. NumPy also has aggregate comparisons. And so the primary ones that you're going to run into is if you use one of your basic comparison operators, you'll get a list, or you'll get a NumPy array of Booleans, and then you can check whether any of those are true or all of them are true using the any and all functions. So for instance, if I have a list of ones, so that's 1, 1, and then I have a list of, I have a range from 0 to 1, then they will not all be equal, but some of them will be equal. I'm realizing I probably should have shown what X and Y actually look like. Apologies. And just to show this can be a little bit more complicated, you can apply an axis. So the NumPy I function produces a identity matrix. So for 3s, you have 1s and 0s. And I can say, I want to find any row, or I want to find all, for each row, tell me whether or not there are any true values in that row. And so in this case, each of them has a 1 in it, and so each of them is true. And then that array I can take, I can take all on and get a single value. I'm introducing here another shorthand. So if I use an array dot any, it's the same as numpy dot any of the array. And same is also true with all. So your logic can be fairly complicated even using these fairly simple structures. Now, you might have more interesting questions such as, are all of my, well, this is basically the same set of questions, but you have the array equal and array equivalent operations, which are going to do basically, sorry, my brain is just fried. So they're going to allow you to check element-wise whether things are true, and then tell you whether all of the values are true. And they may or may not be more efficient than using the individual operators. So suppose again that we have our 1s and our 0, 1 array. I can show you that the okay, right. I don't actually know why this y is here. Okay, so it's just an array of 1s. And an array equal 1 is obviously not true because array equal is checking the shape. 1, 1 is not the same as 1. However, if I want to do array equiv, it broadcasts this 1 to the same shape and verifies that it's true. So array equiv is basically, if not exactly, the same as numpy.all. And then, so this equality is a useful way of for comparing anything that has a definite value. So integers, Booleans, strings, and certain Python objects, because NumPy can represent those in arrays. But where this is all going to break down is floating point comparisons. So floating point arithmetic is inexact. If I want to take the square of 0.1, and it turns out that the binary representation of these two is going to be sufficiently different. So when so the appropriate way to compare floating points is to take the absolute value of the difference and check whether or not it falls within some tolerance. So these two values are less than 1 or 10 to the minus 10, 10 to the minus 10 apart. So we would consider those equal. And NumPy comes with some equivalents to their all close, or to their equality measures. And so if I want to do an element-wise check, I will do is close, and that provides a relative tolerance and an absolute tolerance. And so what this, I'm simplifying here. Their implementation is obviously more complicated, but the basic idea is, again, we're taking the absolute value of the difference of our inputs. And so A and B may be some shapes, or some large arrays, not just individual values. And then I will check whether or not they're within, so ATOL, so that's 10 to the minus 8th, plus the relative tolerance times the magnitude of B. So this allows you to, so when you have very large or very small values, this relative tolerance allows you to consider how close things need to be, and on a sort of sliding scale. And then all close is just applying the all function to the is close value. So there are a couple of questions I might want to see if they're, before we go. So generating data, I will cover in just a minute. Learn NumPy in depth. I don't actually, I would probably check the NumPy tutorials on their website, but I don't know for sure what the best tool, the best place to learn NumPy from scratch would be. Okay. So just to take an example, I stole this from NiStats and then modified it a little bit to fit on the screen. So basically, this is just a numeric, it's a numeric function, and it returns a NumPy array. It doesn't really matter particularly what the various values are, but you have floats and integers in here, and you're using linear spacing and gamma PDFs. So you're going to have complicated things, and so you really don't expect nice round numbers that you can easily compare. And so so if we were to actually get an example result from this, we don't want to compare it to a pre-known, an existing set of values. What we want to do is we want to set constraints. So for instance, what they have is you'll take the result of using a 2-second repetition time, and we want to verify that since it's a convolution kernel, it should sum to 1, which you're going to see that from we're returning the href divided by its sum, so that makes sense. And that for this value, at least, it should be 800 time points long. And you can also make other constraints. So for instance, I know as a double gamma, a difference of gammas is going to have a positive section followed by a negative section. So I might do something like take the sign and check that the sign changes only once. So this XOR, I could go into exactly what I'm doing here. So, okay, I'm taking all but the first sign, and then I'm element-wise XORing it with all but the last sign. And so this is a measure that's going to give me some indication that it will be true if it changes, false if it doesn't change. And so if that only happens once, then the sum ends up being 1. So just trying to give you an idea of the sorts of constraints that you can check without being so specific as to try to check actual values. You may have other ones, such as I want to know what my maximum peak is, what my minimum trough is. Whatever seems relevant to you about the function you're producing is all valid to put in a test like that. Another thing to be aware of when dealing with floats, you can have non-finite numbers. So there are three of these, sort of. There are three types. So there's positive infinity, negative infinity, and not a number, or nan. And you can produce any of these by just dividing 1, -1, and 0 by 0. You'll probably get errors. You will definitely get errors if you don't use NumPy arrays. If you just do 1 divided by 0 in Python, you'll get a 0 division error. So these have their own properties, but they can be unexpected. So infinities are fine, and if you want to compare, if I would just want to make sure this result ends up being less than 2, and the result ends up being minus infinity, that's fine. And similarly, minus infinity is less than positive infinity, and so that works. But the arithmetic really breaks down. So if you divide infinities, you get not a numbers. And in particular, nans can't be compared with anything, including themselves. They just do not equal anything. They aren't greater than anything. They're not less than anything. They may be not equal, but I don't think so. So if one of these shows up in one of your arrays, you can be working with your array as if they're finite numbers and have a sensible algebraic expression that you're testing. But it turns out that a nan or an infinity showing up in the middle of it may stop or may cause it to fail for ambiguous reasons. So yes, I think this is me just going into detail of what I just said. So we can show that our usual equality checks, such as all close, fail when there's a nan involved. So 0 divided by 0 is going to show up in there. And so the isNan function will let you know whether or not an individual value is nan. So just using equality to look for nans doesn't work, but using isNan will. And note the true here, where you get false here. The all close function is very useful in that you can also set equal nan to true. And so now I say x divided by x is close to x divided by x, given that I'm letting nans be equal. And in that case, it is true. So minus infinity equals infinity, positive infinity, or minus infinity equals minus infinity, positive infinity equals minus, or positive infinity. And nans are considered to be true for the purposes of this test. So just to summarize the floating point section, so NumPy provides flexible semantics for comparing arrays element-wise or in aggregate. Floating point arithmetic can violate algebraic expectations, and non-finite values are extreme cases that require special handling as well. And usually, whenever you're doing numeric things, unless you're positive that you've stayed entirely in the realm of integers, you almost always want to check your equality using all close. And you want to pay attention to your tolerances and your nans. So the tolerances that are default in NumPy break down when you have very small numbers. And the results of numeric algorithms may be better tested by constraints than testing that it's close to specific values. One counterexample to this is if you're re-implementing somebody else's algorithm and you have a ground truth, which is the results of the output of their function or their tool. And so you might save that value and then check that when I run mine through, then I get all close to within some tolerance of the expected outputs. So I think I will check to see if there are any more questions there. Looks like Elizabeth is answering quite a lot, so I'll assume that things are being so do you have some suggestion on how effectively test file reading functions? Sometimes I use the same lines of code that I need to test in order to obtain values. Yeah, so this basically, one problem that you can run into when trying to build a test is that you end up writing more or less the same code that you have in your original function in your test, which makes it a fairly poor test, because if that sequence of lines fails, you might end up, or it will probably fail in both places in the same way. I think there's kind of a case-by-case situation there. Sometimes the sensible thing to do is just to say this, I believe this version was correct. I'm going to save the outputs as a file and save that somewhere in my testing directory. Then I will load it up, and at least I'll be able to check whether or not the values have changed since I first calculated this. When there isn't any ground truth, sometimes you just can't do better than that. Hopefully that was a reasonable answer to that question. Okay, so now to generating random data. So when you're generating data for tests, or when you're running tests, you often want, the easy thing to do is make an array full of zeros or ones. But sometimes you want to check whether your method handles anything else. And so random data is a good way of kind of stress testing your functions. It at least checks that they don't depend on getting all zeros from ones. So the current way, and I think this is only within the last year and a half, so NumPy has a default random number generator that they suggest you use. They still have their old numpy.random API, but I suspect they're going to try to deprecate it. And so what we're moving towards is default RNG. And so this is a function that can either be called by itself, or you can give it a seed. So for instance, if you use this seed, which is today's date, you will be able to get these 6 random numbers in order. And so this, I'm just trying to demonstrate that you can get an individual value out, or you can pass in a number of values that you want to get out in one shot. So I do want to say briefly that seeding is kind of a double-edged sword. So the idea of using random data is that you're not sensitive to the specific values, but if you use seeding, you're always getting the same. They're not necessarily meaningful values, but you're always getting the same values. This helps ensure that your test will pass or fail consistently. But if what you want to do is sample the space of possible inputs, you're not really going to be doing that. But the one thing that can be problematic is if you don't seed and your CI just starts failing, once every 3 months because of some particular random number generator, it's going to be really, really hard to track down that bug. So that you're going to need some other approach for handling that case. Incidentally, those kinds of bugs are sometimes called Heisenberg bugs. Okay. So now if you want to generate random data, okay, so here's an example where I may just want to check that for any value I pass to my function, in this case, an arctan, it's always going to fall within minus pi to pi. So I'm going to create my random number generator, and then I'm going, so this finfo just gives me information about float 32s that lets me say I want a uniform random number between the minimum possible float 32 and the maximum possible float 32. Then I'm just going to check that the absolute value is less than pi. So this is okay, but again, we're not really sampling the space very well because we're just taking the first random number that we can get. So we may decide that we want to we may want to decide we want to run 100,000 of them each time and make sure that, if this works, we have a reasonable confidence that the function actually works as we expect. Okay, so random numbers are great, but you may want some more structured data. So there's various ways that you can add structure to your data. So you may want to generate data of a specific shape. So for instance, if you're simulating a slice of a particular image, you may say you want your shape to be 128 by 128. If you want a volume, you may want to simulate something like a T1, 256 voxel square matrix and 150 slices. Or you might have a time series is going to have fewer voxels in each dimension, but it's going to have 200 time points, and so you have a 4-dimensional array. You might also want to use different statistics, but maybe your test is either built for assuming that your inputs are going to have some kind of statistical structure, or maybe it's going to maybe this is a better way to stress the more likely regions where it might fail. So there are a lot of distributions. If you open this up and you click on the ... you'll be able to find the full list of distributions. I suspect in most cases, uniform and normal are going to get you about where you want. So an example for this is if I want to create fake motion parameters, I might use a normal distribution, so zero mean and 1 variance, and I say I want 200 time points of 6 parameters, so translation and rotation in the X, Y, and Z directions. But motion parameters are not they're not temporally independent. That's actually closer to one. You might want to simulate it better with a random walk, so you can use a cumulative sum operation across the rows, so that each time step is motion relative to the previous distance. You may want to generate non-random arrays. So the numpy.full make numpy.full or numpy.zeros or numpy.ones are a good way to generate a large shape of exactly 1 value, which may or may not be very useful. But you can also use scipy.ndimage, assuming you create a useful value, but you want to, you may want to blur it, or you may want to tile it across the space. And there's also scikit image has a number of shapes that you can generate. So they're just all ones on a background of zeros. So and I'll show an example of using this in a little bit. So you are able to produce structure in that way. Finally, you may want to structure things as, so for example, a neuroimage. So here we have Nibabel provides a spatial image API that all volumetric images must share. So if you're trying to write a function that operates on a general notion of an image, then you may want to go ahead and create one of these images. So as an example here, I've created a data object that's 128 cube, all zeros, and then in the middle of it, I'm going to add a ball of ones. And so I'm going to pretend that this gives me a brain mask, just a very bad one. And so I'll create a spatial image that takes this data object, and I'm going to give it an affine of the identity matrix. And so what that says is each voxel is 1 millimeter in dimension, and the origin of this space is in the corner of the image. So it's not a very realistic image. You can make more realistic affines. Now, if your algorithm does assume some more structure, such as we need some of the information that's available in the Nifty header, you can also create specific concrete images that are savable. So just to summarize all of this, you can generate your test data with varying amounts of structure, whether that's the shape, the distributions of values, and at the peak, you can embed in Python objects and make them as realistic as you need to. Generally speaking, you want to try to add the minimum amount of structure needed to test the target functionality. And then I think I will head back over and see if there are any questions. Did I cover Do you have any suggestions for how to effectively generate data for testing? Well, I hope I answered that question. I'm not really going to go into hypothesis, though I will at the end, if people want. I do have like a couple of resource links that will point people in that direction. Is concurrency an issue if using the default RNG method? It shouldn't be. It's, from what I was reading, it's designed to be fairly resilient to concurrency, but there may be specific there are probably some specific well, no, there are definitely specific suggestions for how to initialize it if you're going to be using it in a concurrent context. Are there other questions that should be very urgent before I move on? Because I think I'm actually running a little bit behind on time. Okay. So just as an example, another example for all of this, because this shows a bit of the things I've been talking about, I pulled another test out of Nilearn. And so what this demonstrates is that this comment shows that it's a regression test. This test is failing on master, and in this PR it passes. So this test is generating, or is a good minimal reproducible example that shows here's a test that will fail until I fix it. So it uses a function generate signals, which is actually defined higher in this file because it's being used in a bunch of different tests. And so I have a way of generating signals. And now I create a copy. And using this copy, I'm able to make sure that after running this clean method on the original, that the original hasn't been changed. So I'm checking that the array is exactly equal to the original copy. Now this, we also need to test that when there are nans involved, the same thing is still true. So here we create a new array, which is just a copy of this test data, but we specifically insert a not a number. And then again, we make a copy that should be safe from any modification by the method. So then we clean it again, and then we verify that the original still has a nan by using numpy is nan. And then this is not actually in the test, I changed it, but I think this is what was intended. We can check that the copy and the original are still the same, but we use equal nan is true to make sure that this function isn't sensitive to the presence of nans, which I think kind of brought together a number of the things I've talked about. So hopefully that was a decent example. So I'm just going to try to quickly go through some useful things that are available. And these are more general. These aren't specific to numeric testing. So unit test and pytest. Unit test is within the standard library. Pytest is just a very popular test runner these days. There we go. Okay, so pytest.raises allows you to assert. It's similar. It's basically an assertion, assert statement that says when I run the code that's within this block, I will get this error, and if it doesn't give me, then this test should fail. And I can do that at a higher level by marking a test as expected fail or failure. By saying this, I expect this to fail, and the way I expect it to fail is that it will raise this zero division error. And similarly, if you want to check that warnings are emitted by a certain code, you can use pytest.warns and similar functions. Sometimes you need to skip the test. So there are basically two ways of doing this. You can raise a skip test exception, and unit test and pytest know to interpret that as a skip, not a failure. And you can also use a decorator, which I hope people are familiar with because I don't really have time to introduce the idea, but you can mark a test in this way saying this this test requires a newer version of Python, so don't test if we don't have at least Python 3.5. Useful idiom here from Nibabble is this optional package, which will return the module if it's available and a Boolean saying whether or not the module is available. And now I can create a decorator for each function saying that this test needs h5py, and so skip if has an inverse, which is skip unless. So this decorator becomes a skip if I'm missing h5py, and it will skip it with an informative message. Okay, so fixtures. As a reminder, the fixture is just something that sets up and tears down before and after a test is run. So the way pytest uses fixtures is it passes them as arguments, which is really unintuitive when you first meet it, but it's kind of useful nonetheless. So and when I run, if I say test round trip, which means I'm going to create a file, save it, and then load it, and I want to make sure that the values are the same, or certain values are the same anyway. So I'm going to create I'm going to pass temp path, which creates a new directory, a temporary directory, and now I can create my temporary file, and it's just going to be zeros and not a very interesting image, and I can save it to test.nifty within temp paths. Also, if you're not familiar with pathlib.path, this is how you extend paths using the slash. So it looks kind of like it looks like a slash in your directory. And so now I'll load the file, and I check that the data that comes out is the same, and I check that the affine that comes out is the same. Now, so this is a provided fixture, but pytest also allows you to write your own fixtures, and it's as simple as creating a temporary directory that is going to be cleaned up after leaving this context, and then you yield the path, and that's the value that ends up being passed to the test. I apologize if that's a little mind-bendy or not clear. I would recommend checking out the pytest documentation to see if you can work your head through that out. Okay, you also have parameterization, and this is just basically the idea that if you see a loop where you're testing the same thing over just a set of arguments, you can move this to the outside of your test, and this means instead of one test that can fail the first time f fails to work correctly, it will create a number of tests, and each one will be tested independently. And so you can see, so you don't just fix the first failure, you can try fixing all the failures in one go. I really don't think I have time to get into mocking. I will say it's an extremely useful thing if you need to test something that is either extremely slow or has side effects. So yeah, summary on all this. Exceptions and warnings are part of your API. You can test them with pytest.raises and warns. Skipping tests is useful. I would be wary of using it too much. It may mean that you're not coding to be as flexible as you need to be, but sometimes it's still useful. Fixtures are extremely handy, but also take getting used to. And yes, again, mocks, they're good for avoiding unwanted side effects or testing rare cases. Just one comment on this is, why am I using unittest instead of just using all pytest features? So we recently had to convert Nibabble from nose tests to pytest because nose has been unmaintained for something like 5 or 6 years now, and finally it's going to break with the next version of Python coming out. So the more that you can depend on features that are directly in the Python standard library, probably the happier you're going to be when pytest finally goes to end of life. Okay, I know I'm running late, but I'll just try to blow through these. So with neuroimaging, you're going to have a few things that keep coming up. So orientation sensitivity. The vast majority of problems I've had while coding neuroimaging software is you find two images and they're not actually the same orientation, but you forget to check. So you're going to have various methods that either assume that the orientation is either consistent between two images, or you just assume, for instance, that all of your images coming in are RAS oriented. And this is maybe appropriate for a private method or function that needs to be fast and doesn't need to waste time with checking. And so it's the functions that call it that should be checking this. But this is a good thing to have in your assertions when you're writing your tests. Similarly, things that are in the public API should definitely at least validate the orientation, and they may want to account for it by reorienting the image for the user if that's an appropriate thing for them to do. Another thing that is likely to trip you up is you may write your code assuming that everybody's going to be using nifties, but maybe somebody's going to come along and use an MGH file. And a lot of the same code in NiBabble will happily work with either. And so you may want to check whether or not your software is, or whether your whether your functions are happy to accept the general spatial image API, or whether you need to put in a validity check to check whether that you're using nifty images. So if you want to check your Q forms and S forms and things like that. Oh, speaking of which, there are some quirks of nifties. Nifties have two affines. And so there's the Q form and the S form. This is usually within a piece of software, not a big problem, but when you start moving between software, knowing what is in each of them and possibly making them or syncing them up to make sure they're always the same is a good idea. Nifties can also encode units. So for instance, I can say that my TRs are in microseconds and my voxels are in meters. So you might want to use some tests to check whether or not you're handling those cases correctly. And also there's header extensions. These tend to be software specific, difficult to respect. So one thing if you're modifying the image substantially is to remove header extensions. Okay, so just to conclude quickly, so testing scientific software is essential for good science. At the same time, bugs happen, and regression tests help us move forward. The Python ecosystem has good testing infrastructure. PyTest and unittest provide a good base. NumPy provides a lot of good tools for numerical testing, and you can generate test data relatively simple because Python is a pretty expressive language. And again, NumPy provides some useful tools. These are just some of the resources I took some inspiration from and sometimes copied examples from. So go read those. They probably make the arguments better than I do. And with that, I'll take some questions. Okay. So I think that one is, sorry, getting out of presentation mode and now trying to read. So the hypothesis one, I think I kind of hand waved at earlier. Let me know if there's something more specific you want me to answer. How to approach testing custom neuroimaging data analysis workflow scripts based on external libraries like Nilearn scripts written in Jupyter notebooks. Yes, Jupyter notebooks are hard to test. I think NB-convert can at least be used to automatically run and test the notebooks to make sure that it works. Yeah, I think Elizabeth's going to definitely know more about that than I do. Any suggestions for learning NumPy in depth? SciPy lecture notes. Looks like people got their tutorials in numpy.org are really good. Not really, but could I briefly talk about the difference between fMRI prep and NiPipe? Yes, fMRI prep is built on NiPipe. That's the important thing. So NiPipe is very general. You can make whatever pipelines you want. fMRI prep uses NiPipe to just to organize the workflow, because it's a very effective tool that allows you to pick the best tools from from various suites and help them work together. Coverage statistics. Are there other measures of how good your test suite is? No, I think the best, like what most people use is coverage, and then otherwise it's just the review process. When somebody submits a test, you try to make sure that it's doing what they say. It's not just covering all the lines of code, but it's testing a specific feature of the code that's being submitted.
Okay, if that's all of if you have answered all of the questions, thank you very much, Chris, for this great talk and for answering all our questions. I just put in the conversation the link to the next session, which will begin in 10 minutes at 2:45.
I'm sorry, I didn't give you guys much of a break.
Sorry? No, yeah, we still have time for a break. So yeah, I suggest we close the session now and take a short break.
Sounds good. Thanks a lot.
Thank you again. Thank you very much.